So, good morning, everybody. Thanks for coming out bright and early to Khronos' Developer Day. Today, we're going to be, in this session, we're going to be talking about WebGL and glTF. My name is Ken Russell. I work at Google on the Chrome web browser, and I'm also the chair of the WebGL working group. So, we'll begin today's session with a 15-minute segment on WebGL. Because WebGL is a graphical API, I thought it would be best if we kick things off with some demos. Then we've got some updates. We're going to talk about an awesome new feature and a few new extensions that are coming out for WebGL. We're going to talk about ways that you can take your native applications and bring them to the web in an even higher fidelity manner than has been possible before. And I want to plug the WebGL meetup that's going to happen tomorrow night. So, by way of demos, so this is just a browser, right? And this is a Google Slides presentation. So, of course, all the links are live. Oh, by the way, these slides are already up. You don't have to take any pictures of this. If you search for the WebGL wiki on Khronos' website and go to the presentations from recent conferences, this is linked from there. So, slides are already up. Don't need to take any pictures or any notes. So, this proves that this is actually interactive WebGL. This is Google's Filament physically based rendering system that was originally developed for Android and other mobile platforms, but has been recompiled using WebAssembly and published on the web. And you can see super shiny using WebGL version 2, OpenGL ES3 class functionality, runs great on a lot of devices, including this Razer 15-inch. Recently, a demo came out that some of you may have seen where a crazy individual took the original Castle Wolfenstein and ray traced it using WebGL. Who saw this come out on Twitter a few days ago? All right, like a minority of the audience. And it works great. And like you can actually see soft shadows, and it like integrates the solution, and it gets iteratively better over time. It's got emissive lights somewhere in here. Not that room. We're not going to go into any of the rooms with controversial signage. I mean, no, like evil signage, no doubt. Okay, but anyway, yeah, so you can do like amazing stuff on the web today. The Babylon.js library is getting a lot of cool users. This apartment configurator is amazing. Unfortunately, it downloads a ton of assets, so I think we probably can't like wait for it to render everything. But you should totally check this out because it's amazing. It's doing like soft shadows and light bounces and stuff. And 3JS continues to evolve dramatically, and they've improved their physically based rendering algorithm recently to be more energy preserving, and it just improves the fidelity of all physically based rendering on the web effectively, or at least like 80% of it, because this is what most people are using. Let me just pull this up. Actually, this one's pretty cool. Yeah, so if you haven't seen this like shadow casting demo in 3JS, super cool. But let's move on. All of these, again, are already available to you. So go check them out on whatever device you choose, whatever browser you choose, because WebGL is a cross-platform and cross-browser standard. So by way of updates, what is the WebGL working group doing? We're focusing on conformance again, refocusing on it, if you will. We're trying to get all browsers to pass the top-of-tree conformance suite, and it's been maybe 2 years since we took the last snapshot, and a ton of conformance and regression tests have gone in. This effort's been principally led by James Darpinian from Google, Jeff Gilbert from Mozilla, and Lin Sun from Intel. Many corner cases from the OpenGL and OpenGL ES specs have been uncovered and resolved since the last spec snapshot. And this is going to lead to improved portability of applications, because not only are we finding these issues, we're fixing them, we're unifying the behavior. We've also been spending quite a lot of time resolving bug reports from customer applications and turning these into conformance tests where it's possible to do so and also applicable. And so please, if you're using the API, please keep these bug reports coming through whatever channels are available to you. There's the GitHub issue tracker. If it's a bug in one particular browser, please file it against the browser, and please notify us somehow, because if you just file the bug in the issue tracker, sometimes it gets lost. Email us, or send email to one of the mailing lists, because sometimes regressions do happen. We test the crap out of our browsers, pretty much all browsers, but sometimes things do slip through the cracks. So please Tell us if you see something. So, the single biggest advancement and maybe the biggest news in the WebGL land is that there's now support for compute shaders available. This has been developed by Intel's web graphics team in Shanghai and an army of engineers. They've done tremendous work. This adds ES31 compute shaders to WebGL, and there's a draft specification of this feature online already. You can just click that link. It's already on Khronos' website. There you go. Super cool. And this functionality is available right now in recent Chromium builds on both Windows and Linux. There are some slides here that tell you exactly what command line flags you have to flip in order to get this to work. And the first demonstrations are already out there. Intel has checked in one that does a flocking Boids demo. There are some more compute shader demos from an individual in Japan that look really cool. And please discuss this functionality on the WebGL developers list. So now you can do, GPU-based particle systems and, even artificial intelligence. You can do neural network evaluation, super fast and portably on the web. This is a great way to start experimenting with compute shaders on the web today. And we can promise you that the shaders that you write are going to be well forward compatible with the tool chain, the shader compilation tool chains that are out there to whatever successor APIs come out on the web for doing high performance graphics. So let's talk about some more functionality that's coming in WebGL. One major customer complaint has been, my shaders take too long to compile, my web page seizes up, WebGL is slow. Well, it turns out that WebGL per se wasn't slow. The amount of additional validation overhead that we added on top of the native shader compilation was actually pretty minimal. But the shader compilation tool chains out there, FXC, sorry. The compiler was old, and as a matter of fact, Microsoft's newer DXC compiler for DirectX 12 performs a lot better, but we can't use that tool chain because it's Direct3D 12 only, and the browser is basically built heavily on D3D 11, and there's not a really good forward compatibility story there. So, Intel, in particular, Jia Chen, has been working on implementing parallelized and asynchronous compilations. They work great. Not only do they unblock your main application, but they actually can compile like the vertex and fragment shaders simultaneously, and you get significant speedups. So this is already available as a draft extension in Chrome. Please try it. Please modify your apps to check for the presence of this extension and use it if it's there. It's very easy to do so, very small amount of code change. And basically, as soon as this ships in browsers, your app will get faster. So why not? Another amazing innovation is we've been looking at the almost zero driver overhead credo from OpenGL. It came out years ago now, but trying to figure out what we can put into WebGL efficiently. And multi-draw is the obvious #1 candidate. Can you issue draw calls more efficiently? Can you get better batching? So Austin Eng and Kai Ninomiya from Google have been investigating and implementing multi-draw extensions for WebGL. Effectively, the application receives a GL draw ID variable in its shaders, and you can index into, for example, large arrays. So you can pass down a uniform buffer object in WebGL2 and send your per instance data in there, or per draw call data in there, and then just index into the array based on GL draw ID. And there are tremendous speedups available here. I mean, you can see this micro benchmark called Anemometer, which Apple came out with a few years ago. It's doing the most inefficient thing possible. It like sets some uniforms and draws one triangle. Sets some more uniforms, draws another triangle. And does that like 30,000 times, all right? That got like 70 times faster with this, just by batching up all the draw calls into, the draw calls uniforms into one uniform buffer object and then sending it down in one call. I mean, it's sort of staggering that there was this much of a performance gain to still be had in the browsers, but we're seeing this on multiple implementations. Safari had Austin did a prototype in Safari, and also got a significant speed up there. So we're expecting to ship this extension soon. Think about how you could better batch your draw calls, and you'll see some significant speed ups in your apps. You can try it today. It's in Chromium. Just turn on that enable WebGL draft extensions flag, and it's on all platforms. This is emulated where the native driver doesn't support it, and it's still a big performance win. And let us know how it's working for you. We really want to hear back from you. Another significant improvement is video to texture uploads. A lot of folks are doing 360 video in VR, or trying to, and maybe seeing performance problems trying to do this on the web. And we hear you loud and clear. We've been working on getting zero copy texture uploads to WebGL for a while, and this extension will do it. It's being once again developed by Intel's web graphics team in Shanghai, in particular Xiaobao Yan, and the implementation is landing in Chromium now. It's going to be behind the enable WebGL draft extensions flag again. We're seeing 47% speedups on some content. We actually expect more speedups as we evolve the implementation. So please try it out and give us your feedback on Khronos' public WebGL list. So, who knows what WebAssembly is? All right, so WebAssembly, if you don't know, is a technology that lets you compile native code, be it C, C++, or for example, Rust, into a platform-independent binary representation that the browser then ingests and runs in a sandboxed manner. And the cool thing that's coming out right now is that threading support is finally here. So you may have heard about the Spectre and Meltdown attacks that came out against like all CPUs in existence last year, and that was kind of a bad time. But the browsers so the implementations have been hardened, and better separation is being put in place between different web pages, and that enables this multi-threading to be safely put into implementations. So basically, you can now take increasingly complex real-world C and C++ code bases and just compile them for the web, and it just works, kind of. I mean, you have to make some, changes, but yeah, it pretty much works. And we can tell you, and we're happy to tell you that both Unreal Engine and Unity have HTML5 export paths. They have for a number of years. They've upgraded to WebAssembly, so they've ditched the old Asm.js implementation. And both of them have experimental threading support already, and we are partnering with them actively to resolve all the remaining issues in this to make sure that it's going to be like seamless, smooth, and really competitive with native performance. You can even access this from Rust. So there's a blog post out there that shows how to do multi-threaded Rust and then compile it to WebAssembly and run it in the browser, and it's really cool. This is a game changer. I mean, this is the way that you're going to get like millions more eyeballs on your games, because the friction is going to be gone. You're just going to go to your web page and you're going to be playing the game, and it's going to be exactly as it is on whatever other desktop or mobile deployment you've already got of your game or your engine. And it's really, it's sweet. So give it a try. Please report any bugs that you encounter. You can always email us or post bugs on, for example, the Chromium issue tracker. So this work wouldn't be possible without just an enormous amount of time and effort and energy invested by, for example, both the WebGL Working Group regular attendees and Intel's web graphics team in Shanghai. And I want to thank everybody who has contributed to these advancements, and we really look forward to continuing to deliver them to you. And again, let me please plug tomorrow's meetup. It's at Galvanize on Tehama Street. It's really just a few blocks away. 6:30 to 9 p.m. And if you haven't pre-registered, please do. It's going to be a great event. Khronos is very generous in hosting it. There's going to be food and drinks, so please come, eat, drink, and be merry. And so please hold questions until the end of the presentation. And now Patrick Cozzi will lead the glTF portion of the session.
Awesome. Thank you, Ken. Great. Yeah, I love the progress being made in WebGL. I'm excited about compute shaders, multi-draw indirect, WebAssembly threads, everything Ken just showed there. Very impressive. I'm very excited for. So as Ken said, my name is Patrick Cozzi. I work on the Cesium team at AGI, and I'm also the chair for the 3D Formats Working Group at Khronos, working on glTF. And I'm going to do a quick, maybe 5-minute intro to what's new in the world of glTF, and then we have a bunch of lightning talks from the people who are making this all happening. So how many people are familiar with GLTF already? Okay, about 3/4, that's great. So GLTF is an efficient runtime 3D asset format, originally started for the web, for WebGL, and now being used across all different APIs and all different parts of the pipeline in terms of we have tools that are exporting GLTF, many rendering engines that are ingesting it, and then many tools for doing optimizations, validation, and so on. This is the current state of the ecosystem, a subset of the current state of the ecosystem. And I want to share some recent highlights. So in the tooling world, the Blender 2.8 beta is shipping with GLTF import and export. It's super exciting. Then we have really high-end tools in the VFX world, Cinema 4D and Houdini that are now supporting GLTF as well. TurboSquid now exports GLTF, which gives you access to over 700,000 assets, really impressive. We're also doing work with other standards organizations, including OGC, the Open Geospatial Consortium. Our liaison relationship there resulted in the 3D tiles format, which basically puts a spatial data structure on top of GLTF to support massive scenes. Then both Google and Mozilla are doing AR and VR work, all powered by GLTF. So there's a few key initiatives that Khronos has been working on that I want to share. The first is the official Khronos GLTF sample renderer. So we recognize with lots of different renderers out there importing GLTF that users want some level of consistency among those different renderers. So this open source sample renderer is a great sample to look at when you're implementing your rendering engine and helps us really define, okay, well, what are the PBR materials? What are the formulas? Where can things differ? Where shouldn't they differ? And we're still ironing out some of the fine points here, but we feel that this will go a long way, and you'll hear more about this with the upcoming speakers. So the next big thing is I'm really excited for when we brought PBR to GLTF about 2 years ago. I really think that helped bring GLTF cross-platform and also helped bring PBR to the web. However, we're getting a lot of feedback, particularly from the retail world, that we need to take the PBR materials to the next level. We need to support things like absorption, clear coat, subsurface scattering, and so on. This is a really interesting challenge for GLTF, where we want those assets to be able to run everywhere, but still have very high quality rendering. So part of the work here in defining a next generation PBR model for GLTF is not just defining the parameter set, but also what are the reasonable fallbacks if you're going to support anything from ray tracing to desktop rasterization to mobile. The Dassault Systems, they have a really nice enterprise PBR shading model that we're taking a lot of inspiration for, and hot off the press, was it last night or the day before that, they did put out the start to a draft PBR extension for GLTF. So, the call to action here for everyone in the room is we would love to have your input in terms of what you'd like to see in next generation PBR, what you think about the parameter set that we're currently looking at, and then if you're doing any PBR rendering in your engine, we'd love to talk to you about it. Right now, there are a number of folks listed here that we are working with. The final big update I want to share is in the world of textures, both the KTX2 container texture format as well as CTTF compressed texture transmission format. So the KTX2 is a container that can hold your textures in your various MIP levels, and the latest version of that is available for community feedback. It is not yet ratified, so it is a great time to check out the GitHub link at the top of this slide here and provide your input. Part of our motivation for KTX2 is to support this TTTF for universal texture compression. So instead of having 3 copies of your model GPU with the textures compressed in 3 different ways for 3 different GPUs, you can have one super compressed texture that then at runtime is transcoded to the GPU format. So you get JPEG-like compression over the wire, and then you still get GPU compression. There is a prototype open source codec in the GLTF texture transmission tools GitHub repo, and then the specs will follow here. In terms of things that you, the community, could do to help, we really need some additional help around doing the open source tooling here. would be very happy to collaborate with the folks in this room. Okay, so the last and most important thing I have to share is our speakers today. So the folks up here are very involved in the GLTF community, in the GLTF working group. Saurabh from Microsoft will give us an update on the Microsoft ecosystem where GLTF has spread far and wide. Chris from Google will talk a bit about the model viewer web component and some consistency-related work. Mike from Adobe will talk about dimensions and GLTF support there. Robert from Mozilla will talk about GLTF in Mozilla Hubs for VR. Par from Facebook, unfortunately, is sick in his hotel room right now, but he sends his best wishes and his good energy. And his colleague, Susie, is on her way, and she will be here by the time she has to tell us about using GLTF at Facebook scale. So with that said, I do invite all the GLTF speakers to come join us. And Saurabh, I'm going to turn it over to you. Thank you.
Thanks, Patrick. These slides should be up very shortly. I think Ken was already up there with the WebGL slides. We'll be posting the GLTF slides very soon. I'll start off by giving a quick whirlwind update of where all Microsoft is using GLTF. Starting with Office. There's 3D in Office now, like this little astronaut. But now we've added more. We can actually have animations in there, so the astronaut can wave back at you. Or you can make the astronaut run around on the slide. But he's running a little too slow there because something's kind of following. So I was just having a lot of fun with this last night. But really, we see 3D and animations being used a lot, especially in the education space, where you can really see an animated object on a slide and kind of get the messaging across on how things work. So that's 3D in Office. We also have SharePoint Spaces, which is mixed reality for the workplace. All the models there are GLTF models. If you ever search for things on Bing, there's 3D ads now on Bing. So the latest phone out there isn't available in 3D, also a GLTF model. OneDrive, if you have 3D objects on your OneDrive, we let you preview it, whether it's on the web or on mobile. It's all GLTF. We have a default built-in 3D viewer in Windows, and it's actually gone through a big overhaul where now you have some advanced capabilities in there. You can inspect different textures, look at bones, look at the various material models. So all this just kind of comes baked in as part of Windows. We also have some developer stories around this, starting with Allspace VR, which is a VR social network. They have a new SDK that is using GLTF as their primary input of models. Those are the sample models out there. But you can then go really beyond with this SDK, where this whole chess game is just a bunch of GLTF objects. And of course, there's logic that you have to add as part of the SDK, but it's all kind of enabled by GLTF. We are improving our developer story too. We are bringing more APIs to Windows where we want to make 3D more accessible. So we'll have simple GLTF file loaders, so give you some basic 3D controls, and then have an easy interop between UI and a 3D scene graph. All this is kind of available as an insider preview at that link, which you can go kind of check out later on. So a lot of this work, we also use Babylon.js to power a lot of our products, and all that work is done in open source. Really, we want to encourage adoption of the format, and that's why we do it all in open source through the kind of the Babylon.js effort. Babylon.js is, of course, the engine. You saw some demos of it already during Ken's presentation. A lot of the experiences that you saw earlier in the videos are powered by Babylon.js. But we also invest in a lot of tooling around GLTF and WebGL through this effort. We'll be talking more about this at the WebGL meetup if you're interested. There's specifically the 3ds Max Exporter and VS Code debugging tools for GLTF, which help you adopt GLTF more. So finally, I kind of want to end with some kind of inspirations for what Patrick was talking about with PBR Next. We want to explore additional material types, and we are kind of doing it in collaboration with everyone. It's all open source in Babylon.js. So here are some examples of how Sheen could help with fabric materials. Again, this isn't really a spec. These are explorations. We are trying to do, make it work in the engine, make it work on the web. This is all just WebGL. And then we learn from that and kind of push it into the next BBR, next spec. So that's clear code and Sheen. I'll finally end with, it's very important for us to make sure that everyone consistently, oh, that's a quick video, adopts GLTF consistently. And there's a Khronos project called GLTF Asset Generator, which has about 150 or 180 GLTF models, which help you test out each and every aspect of the GLTF spec. Right now, it's got this rudimentary viewer where you can load up the spec. It's got animation support and things like that, and you can test it out across different engines. There's some work that Chris is going to talk about next, which kind of takes it to the next level and helps you even kind of visually check across multiple engines. So with that, I'll hand it off to Chris.
Hi, all right, I got about 10 minutes of slides and 5 minutes to talk, so it's gonna go kind of fast. Hi, I'm Chris. I'm a software engineer on the Chrome team. I work on a project called Model Viewer, and I'm here to talk about fidelity testing and how we use it in the Model Viewer project. And just to give you a quick background, because I don't have a lot of time, Model Viewer is an HTML web component. A web component is just a custom HTML tag. The Model Viewer HTML tag makes it really easy to put 3D assets on the web. You know, just like you would put an image on the web today, you can use Model Viewer to put a GLTF on the web. It gives you all sorts of cool things, responsive layout. It's very conceptually similar to how you would think about other HTML nodes. And you can configure it with attributes. You get all sorts of cool stuff like fallback for iOS Quick Look, holograms on Magic Leap. It even has experimental support for WebXR. Definitely check out Model Viewer. It's on GitHub. As we built Model Viewer and we took it around to different people who we thought might want to use it, and I'm talking about like e-commerce, people with portfolios where they want to put their art online, the number one thing that we kept getting asked was, well, if I use Model Viewer to present my art or my product or whatever to my users, is it going to look the same in Quick Look? Is it going to look the same in Google's Filament, for example? And we found that we had no great way to explain to them, like, oh yeah, we're striving for rendering consistency. It's GLTF, it's standard format. It's going to look the same everywhere. It turns out that this is just a really hard problem. For any given model across multiple renderers, there's no guarantee that you're going to get consistent rendering. Different renderers, they have incorrect interpretations of GLTF. They have inconsistent opinions about what to do with lighting, things like environment lighting or maybe post-processing or shadows. These things are just not specified in GLTF. And there's unpredictable fallbacks. So what do I do when the GLTF is malformed? Turns out a lot of people are not producing GLTFs today, and so when they go to do it, they may have problems in the model format that they export. Being a web engineer, I thought, well, why don't we just automate this? We'll just write tests. It's really easy. We do all sorts of cool stuff on the web with taking screenshots, comparing it against different browsers. It seems like it's in our wheelhouse. So let's just write tests. Easy, right? Well, okay, not so easy. We put together a little design proposal and said, okay, look, let's take Filament, it's a great renderer. Let's take Model Viewer, let's take screenshots of these things and compare the two, do some light image analysis. At the beginning, it wasn't really much to look at, but we cobbled together a nice comparison tool. It's all web-based, and we were generating these screenshot artifacts based on our CI automation. And it was kind of nice. We could look at two different renders and then compare the two and just eyeball and see where the differences were. Where it really started to get interesting was when we added support for HDR environment maps. We added support for radiance maps in a Model Viewer, and we were getting really closely comparable renders between Filament and Model Viewer. And by the way, Filament was just the renderer that we picked to start out with because it was within reach. We knew some of the engineers on the team. Anyway, we were taking all these screenshots of Filament, and we noticed, oh, look, there's little details that we can call out, and maybe these are discrete problems that we can start to fix. There was some highlighting that we saw in Model Viewer that we weren't seeing in Filament. Directional light had a certain radius in Filament that was different in Model Viewer. Turned out the environment map is like turned 180 degrees around in one renderer compared to the other. And like if you look on the Filament side, there's like muted emissive on this model. So we'd written this test and we looked at it and we thought, wow, this was really useful. There's lots of little discrete things we can pull apart and try to fix. Wouldn't it be cool if there were a bunch of models like this that all test discrete little use cases in this model format? Turns out there is. There's a great repository of awesome sample models that Khronos maintains. And so the next thing we did was we took all of those sample models and we wrote fidelity tests for every single one of them, threw them in our comparison tool, and voila, we had all these awesome artifacts that showed us these are all the discrete differences between model viewer and filament. So we took these test results and we started breaking them out into issues, and I just want to run through a bunch of the stuff that we were able to fix. So it turned out filament didn't have good support for 16-bit per channel pings. That's been fixed. They didn't have support for normal tangents, been fixed. Unlit materials, turns out we weren't doing the right thing, it's fixed. Alpha blending support, fixed. And emissive that I showed you in that slide earlier, fixed. So after all of that work, and by the way, that represented maybe 6 to 8 weeks of work. Was it worth it? You might remember this slide at the beginning. We had all these little artifacts that were wrong. This is what it looks like now. Looks pretty good. You can clap. And look at that emissive. If you put a gun to my head, I don't know if I'd be able to tell you which one was from which renderer. And back to our humble beginnings, this was the PBR spheres that I showed at the beginning. Hard to tell them apart. They look really good. And because we do this as part of our automation flow, it generates an artifact that gets put up on GitHub pages every time we do a build on master. So if you click on this link, and I'm sure the slides will be available somewhere, you'll see the live comparison viewer, and you can check out the results for yourself at any given time. So where do we want to take this in the future? You heard about the Khronos sample viewer that is being worked on. We want to integrate that into these tests. We're looking for a solution for iOS Quick Look because a lot of people in e-commerce, for example, care about iOS Quick Look. We don't have a good way to automate screenshots for that. We want to do an interactive progress report dashboard so that we can say, this is how all the renderers compare to each other over time. And finally, we'd like to break this out into a standalone testing effort because this is a problem that everybody's going to face when they start to put their 3D content on the web. And so we want to just make it easy for them. And that's all I got. Please try out Model Viewer. Thank you.
Awesome. Thank you, Chris. Next up, we have Mike from Adobe.
Hey, okay, so I'm just going to give a quick update on Adobe Dimension and what we're doing with glTF. We launched Dimension last year, for anyone that hasn't heard of it. Just a really super quick overview of what Dimension does. We're targeting Dimension. It's a 3D tool that does offline rendering, ray tracing. It's mainly targeted at professional graphic designers who don't have any prior experience with 3D. So we're super simple tool to kind of give these designers the power of 3D and change workflows that can really benefit from the power of 3D. So as an example, product workflows that would traditionally be done in Photoshop or Illustrator and then be printed out and done with physical mock-ups and a lot of then photographs can now be replaced entirely with digital 3D renders that can be easily iterated on. So yeah, we have a lot of companies that are doing product shots and package design, but also a lot of artists who are just creating cool stuff, doing beautiful renders. And then last year we added export pipeline, which we're calling our publish feature, to glTF for real-time web-based viewing of your Dimension products or projects, which enables really fast review and iteration. So here's a Dimension scene, and right away, the problem we had, of course, is that we want to reproduce this this project in a viewer as closely as possible to what you see in Dimension. And glTF by default doesn't have any background information or lighting or anything like that. This is what the viewer looks like now, which, as you can see, so this is WebGL. What we just saw a second ago in native Dimension was OpenGL, and it looks pretty darn close. You get all your camera bookmarks, you get your background, you get all of the lighting. You can navigate the scene. It's a pretty simple viewer. It's still in beta. There's not really too many features yet. This was developed last year, and so to do this, we helped define a couple of extensions for the punctual lights extension, so point lights, spotlights, directional lights, as well as we worked with Microsoft on an image-based lights extension, which will hopefully get in the near future transitioned into a Khronos ratified extension for image-based lighting. And along with a few other extensions, I helped define or I did define a vendor extension for thin transparency, so that does absorption and scattering and refraction. And getting back to what Patrick talked about earlier with PBR Next, a lot of these features will hopefully make it into a ratified extension at some point this year. I can replace the vendor extension. This upcoming soon, and at the beginning of April, we're releasing Dimension 2.2, where we've added substance material support, where you can import any of your substance materials and adjust them within Dimension. And then with that, you get, of course, export to glTF materials. And I've also added importing glTF and GLB, which makes it easy to pass around fully PBR models in and out of Dimension. And later this year, going to get the web viewer out of beta, support animations on import and export from Dimension, and we're still exploring different export routes, so not just publishing to our viewer, but to other platforms as well. And of course, looking at the compressed texture support. And we're also helping out with the PBR Next effort. Mainly, I'm going to be looking at displacement and transparency, since those are the things that Dimension most needs from glTF right now. But we'll also be interested in other things, especially with our integrations with Substance now. Yeah, I think that's about it. I just wanted to give a quick shout out to the Microsoft guys. We're using their open source glTF SDK for importing and exporting. Makes everything so much easier. Yeah, and then we have a pre-release channel for Dimension. If you want to, you can hit that link there or email me, and you'll get a lot of the glTF stuff is in pre-release right now. Yeah. So next up we have Robert.
Hi everyone, my name is Robert Long. I work on the Hubs team at Mozilla. Today I'm going to talk a little bit about how we're using glTF in Hubs to publish virtual worlds. We released Hubs in last year around April, so it's been about a year now of development. For those who don't know anything about Hubs yet, Hubs is a social VR app that runs in your browser. You can go to hubs.mozilla.com today and create a new room with just a single click. Once you've created a room, you'll be presented with a little invite dialog where you have a link that you can share with anyone via Discord, Slack, text message, email, Reddit, wherever your group is. Then they'll join the room with you, and you can talk, import 3D models, images, and videos. You can even share your screen or stream live video from things like Twitch. It works in VR on both desktop headsets like Oculus Rift, HTC Vive, Windows Mixed Reality, as well as standalone headsets like Oculus Go. It also works in 2D mode on both PC and your phone. In fact, a majority of our users use Hubs in 2D. So how are we using glTF in Hubs? We use it for just about everything that you see. All of our interactable objects are glTF. If you haven't figured out by now, we really like ducks. We added support for searching and adding glTF objects from places like Sketchfab and Google Poly directly inside Hubs. We also use it for all of our avatars. Right now, we have a variety of different robots. And we're about to support skinning your bot avatars with your own textures. If you notice, these are the same maps that are in the glTF PBR material. So we store all of those textures on our servers, and then at request time, we actually mix them into the bot avatar and serve them up right there. glTF is just JSON, so it's really easy to implement this feature. So we provide everyone with this UV unwrap template with all the different bot parts in their own layers. It's symmetrical, so it's easy to open this file in your favorite image editor and paint while mirroring horizontally. Here's a few examples of things that we've created so far. We're really excited to see what the community comes up with. One of our artists, Jim Conrad, had a lot of fun creating his own avatar, JimBot. We also support uploading your own GLTF file to use as your avatar. Our avatar skeleton is roughly based on the high fidelity skeleton. We currently have most of this working with the Blender GLTF exporter, and we'll be releasing resources for creating your own avatar model soon. Despite it being somewhat tough to create your own GLTF avatar, we already have a couple of our dedicated users creating avatars right now. We also use GLTF for all of our environments. To create these environments, we developed our own editor called Spoke. Spoke can be used to create hub scenes from your own GLTF assets or using assets like Sketchfab and Google Poly. It's browser-based. It currently ships as a desktop application, but soon we'll be releasing a hosted version of the editor so that you can get started even quicker. Spoke also has the ability to add lights, set animations, and add behaviors to your scene. All of this component data is actually stored in the GLTF itself and then loaded as A-frame components when it is published to hubs. In addition to models and component data, you can add additional media such as images and animated GIFs, as well as videos and Twitch streams. And it's all available in the Spoke editor itself. Spoke has a simple flow for publishing to hubs with just a couple clicks. When publishing, we also generate a navigation mesh for your environment, which we use for teleportation around the map. We add attribution information, so all of these assets that you pull in from other places get credited. And we optimize these GLTF models by combining meshes and deduplicating materials. And then we upload it to our servers. Here are a few examples of scenes our users have created with Spoke. And these are all using some custom models, but mostly assets from Sketchfab and Google Poly. So to wrap up, we'll be shipping custom avatar skins soon. We'll be releasing resources for exporting your own avatars with the Blender GLTF exporter. We'll be shipping the hosted Spoke editor. We will also be shipping a Hub's Discord integration. We have a bot that we're building so that you can communicate with people inside of Hubs and they can communicate with you and create Hubs rooms and stuff like that, and a whole lot more features. So thank you so much. You can go and check out Hubs today at hubs.mozilla.com. All of our code for Hubs and Spoke and all of our backend services is open source. You can go to our GitHub. You can follow us on Twitter. And I'll also be talking more about some of the technical details of Hubs and Spoke at the WebGL meetup tomorrow night. Thanks.
Great job. Thank you, Robert. Our last GLTF speaker is Susie. She made it here from the train on time. Thank you very much. If you just hit the next arrow, you'll be.
Okay. Hello, I'm Susie. Sorry, my co-presenter Zhao is not feeling well today, so I will be giving this talk. Bear with me if it's not perfect. So I'm gonna be talking about what's the recent work we've been doing on GLTF-centric work on the backend to serve 3D model to the client on request in a scalable and future-proof way at Facebook. So about a year ago, we introduced the 3D post feature where the user can upload a GLTF 3D model to their timeline and groups and so on. And as part of the ingestion phase, we simply break down the model to the raw data level like the vectors of the vertex positions, node graphs, and so on. From then on, we can easily do some optimizations from simple things to complicated and time-consuming things like mesh decimation. It becomes a clear idea that we want the ability to serve the different clients with different variant of asset. So depending on all kinds of factors like the hardware capability of the client or the network condition at our best guess, it would be great that we don't need to try to work out the variant configurations beforehand, but instead we can adjust them later and add more to them later. The obvious answer will be serve the client and build the variant on the fly. When a client requests an asset, we just look up internally for a variant which is have the exactly right configuration. If it exists, then we serve it to client. If not, we simply build it on demand. The system is delightfully future-proof because we can keep adding new client in the future, and we can add optimizations that become retroactively enabled for existing assets. And perhaps the most critically, we can do some quickly deployed server-side workarounds if we find the client bug. Then half a year later, we introduced 3D photos. This is basically just a 3D model, but normal users can upload as long as you have an iPhone with a depth camera. So one of the first things we noticed that with the uncompressed texture become so expensive, use too much memory, that older phone become crash more often. So the answer is obvious. We should use compressed texture formats. And then last year we introduced an internal service for texture compression. And 3D photo becomes more and more popular reasonably, and also at peak time we found ourselves need to compress hundreds of textures per second. So how we scale? The answer is easy. Why not we cache the texture that got compressed, and which can be reused on different variations on creation for different clients. And this is especially useful when we roll out new configuration feature for variant. At that time, we have to regenerate all the variants, and this will not be done all from scratch because we have the texture cached. And another important thing we improved last year is we extend the backend system for broader adoption to generalize the infra to be the 3D infra to power up all the applications across Facebook. As more and more new products are using glTF, we started with 3D post and then 3D photo, then Oculus Home user-generated content, and more to come. We have some ongoing challenges. First one is more like the format, glTF specification requirement. Especially in a commercial product model, a model can have, like for a sofa, it can have different color, different it can be leather or fabric, right? So we want to have a single asset to hold all the variations of the color and or the materials, but share the same geometry, so that one single GLTF can do that. Then the next thing is as we have more and more VR applications, we want to stream the textures and geometries, and we would like to do also mesh decimation, because the latency is becoming a more important issue in here. Thank you.
Great job. Thank you, Susie. And thank you once again to all of our GLTF speakers and to Ken for speaking about WebGL. One more round of applause. So it's a very rare time that the GLTF group didn't go to the very last minute, and we actually have about 8 minutes for a Q&A session for anything related to GLTF or WebGL. So who has the first question? Yes?
I have a question about WebGL and WebAssembly. It was mentioned that there is an option now to have multi-threaded WebAssembly work with WebGL, and I was wondering how well does this work if you are planning to use traditional JavaScript interacting with some kind of WebAssembly module. Would that still have a good performance, or is there some kind of overhead?
Yeah, so the question was, in the multi-threaded WebAssembly case, how well does it interact with JavaScript? It works well, it works fine. So the JavaScript has had kind of multi-threading support for a while, web workers. So independent JavaScript can run on different threads in the browser. They can't really interact very easily. You can transfer objects between one worker and another. It depends on the threading model that you choose for your engine. You can move all your rendering off to another P thread, and whenever it produces a frame, it gets picked up by the browser, independently of the browser's main thread. That is a rendering model that is now available. We're still doing some iteration on the specifications for this, but like the basic spec for it is there now and will be portable between the browsers. So basically, you could do some JavaScript on one of those background workers. You could do it on your main thread. You could send information to a background thread via the shared memory, which is the application's C heap. Plenty of ways and options to do it. It all works well. And all the browsers are optimizing both calls in from JavaScript to WebAssembly and WebAssembly calls out to JavaScript. Yep.
Very cool. Who has the next question? Right here.
How much of the CTTF toolchain is done right now? Like, can I take JPEG and spit out CTTF, and on the client spit out EPC, SPPC, and so on?
So the question is, how much of the CTTF toolchain is done and available today? There is a prototype on GitHub with the link that I shared previously, and I believe it does conversion just to ETC1. I don't know if anyone else in the group knows more about CTTF than me.
Maybe somebody in the audience does.
So I think that's the current state of the tool. There's still more work being done to formalize the spec and the schema. But yes. Yeah, and the folks from AMD has been working on this. I'd be happy to put you in touch, especially if you want to contribute to the open source. Next question?
Somebody over there.
Sure.
So the question is, what is WebGL's plan for Vulkan and Metal support? There's another specification effort that is sadly not being hosted at Khronos, called WebGPU, and all the browser vendors are at the table there, and that's defining a new API for doing web graphics that's lower level than OpenGL ES. So I encourage you to join that community group. Anybody can do it. It's just a click-through agreement, and then you can join in on the conference calls.
So I'm wondering, what's the future between WebGL and WebGPU?
So the question is, what's the next generation between WebGL and WebGPU? Well, I mean, WebGL is not going away. Okay, all the browsers support it. We are working on universal support for WebGL 2 as the baseline for doing graphics on the web. You know, the browser's not going to just drop support for it. Okay, it's had a tremendous, you know, there's been a tremendous synergy between the developers that are producing amazing content with it and the browsers that are implementing the API. So we're going to find ways to bridge the two APIs. I wouldn't be surprised if we have some kind of texture sharing, you know, API between them, or some way to, you know, publish one canvas, you know, live into another one or something, you know. You know, there may be options for even bridging between the two at a more fundamental level. Because if WebGPU is a pretty low-level API in the spirit of, you know, Vulkan and D3D12 and Metal, and it's efficient enough, you could actually imagine implementing the OpenGL ES state machine on top of it. Like Angle, yes, like the Angle project does. So there's some pretty interesting possibilities out there, especially with multi-threaded WebAssembly.
Was there another question in this area? No. Other questions? Yes.
What are some of the speed bumps in the process that you're aware of to converting the existing desktop C++ application to WebAssembly?
What are the roadblocks in converting a desktop C and C++ app to WebAssembly? You really need to have an OpenGL ES backend for your desktop app. And a lot of desktop apps are coded to desktop GL specification. The differences aren't that major, but you've got to sort of make it work. A good way of testing that locally in your desktop app is taking the Angle project, which implements OpenGL ES on many platforms, and plugging that into your desktop app first, getting that working. And once you've got that working, you can pretty much compile the thing out. The other issue is the rendering model. A lot of people are used to having an infinite loop that does like take input, swap buffers, take input, swap buffers. We don't have a swap buffers API for the web. Okay, we tried, and it got rejected in the standards process. So we've been trying a couple of other alternatives. The portable way of doing it is using an mscripting trick, where you basically, so the C threading model is you set your main function, and you run the thread, and it never returns. On the web, you're really not supposed to never return from threads, but you can in WebAssembly. However, if you want to render from a background thread, you have to set up mscripting in such a way that your main function gets called many times. It's not a big change, not a big architectural change typically, but you have to do that today. And then that background thread will actually get ticked with the browser's request animation frame callback. And that's how the frames get published. So it's fairly small surgical changes to your C++ app that get you in multi-threaded mode onto the web. Yeah.
Who has the next question? Last call, any other questions for the session? Yes? The question is there a plan to have one standard GLTF exporter for preferably command line? So I don't know that we have one standard exporter. We do have a GLTF validator that, given a GLTF model, it will tell you if it conforms to the spec or not. And then we do have tools like the sample render to see how something renders. Then there's also a VS Code plugin to see how a model renders in different engines. In terms of exporters, we have funded projects for converting Collada as well as, and then Facebook has done FBX, as well as the Blender exporter. And they're getting, especially the Blender ones, getting pretty heavy use and a lot of active development and bug fixes happening in GitHub. You know, we do see glTF, in order to really fulfill the vision, we have the ecosystem has to be super robust. So if you run into any issues with any of these exporters, you know, please submit issues to GitHub, and you know, we'd be happy to collaborate. Okay, I saw a sign came up that said we had 1 minute, but are there any other? Who has the final question? Okay, so the speakers will be up here if you want to come talk individually with us. Once again, thank you all for coming, and thanks again to all the speakers.